cases. Our group members listed here came up with several science cases that will require the access high spatial resolution and a large effective area concerning feedback from star forming activity. So stellar feedback science is relevant to ASTRO 2020 decadal survey. We try to understand how do the star forming structures arise from and interact with the diffuse ISM? How do gas metals and dust flow into, through, and out of galaxies, and which sources reionized the universe? Normally, in non-Asian star-forming galaxies, X-ray emission is dominated by hot gas and X-ray binaries. Here is the optical and X-ray image of the nearby star-forming galaxy M83. The right figure is the Chandler image of this galaxy, one of the best and deepest X-ray data among the nearby galaxies. And you can see that hot gas exhibit some of the spiral-like features that can be seen in optical image tracing an H2 region appear in the red on the left figure. So in this talk, I refer to the stellar feedback as the feedback from hot gas, studying the first two science questions in the previous slide. How do star-forming structures arise from and interact with the diffuse ISM? And how do the gas metal and dust flow into, through, and out of the galaxies? With X-ray binaries, we'd like to understand how feedback from X-ray binaries affect the intergalactic medium during an epoch of heating and regulates production and or escape of the ionizing photons during reionization. So now I start with feedback from hot gas. Here is a cartoon figure of the very basic idea of how hot gas is created from the star-forming activity. The left figure is the side view of the star-forming region. And the grayscale indicate the cold gas density, and darker gray color indicate the galaxy disk. So stellar winds and stellar supernova deposit energy into the surroundings, creating a shell, and superheated gas from this supernova interacted with the cold gas, create and filling the cavity with the hot gas. If this bubble has enough energy, it may expand and then break out and create a hot gas outflow. Left, this one is the brightest H2 region of the nearby face-on galaxy NGC 243, and you can see the star clusters in the middle, then edge alpha shell appears in the red, and hot gas is in blue is filled in this H2 region. So this is one of the example of the feedback on small scale, but feedback can be seen on the various spatial scales. So starting in the top image, H2 region has the physical scale of a few times 10 parsec to the several 100 parsec. Here is the deep chamber M83 image. It shows the hot gas from the collection of the star-forming region tracing the galactic structures. And the left is the M82. If the star formation is very intense, like starburst galaxy here, the white ellipse is the optical extent of the galaxy, and you will see a kiloparsec galactic wind coming out of the galaxy, removing the material from the host galaxy. But this slide illustrates the difference in how AGN and stellar feedback operates. Left picture is the smoke coming from a cigarette representing an AGN feedback, meaning one dominant source is creating an outflow, and we can try to trace back from the outflow material to get the information like energy and the momentum of the single source AGN. However, stellar feedback is like a flock of a bird creating a big bird. So right figure, this is the actual photo of the flock of the birds that you can Google and find over the internet. The transfer of the energy or turbulence happens from the small scales of the motion to the large scale of the motion. And in this stellar feedback case, it isn't straightforward to track back from the galactic scale outflow to the feedback on the individual supernova explosion. So we want to study stellar feedback on the star cluster and H2 region scales. These are the scale of the feedback actually operates in star-forming galaxies. But one of the problems with studying hot ISM in individual star-forming galaxy, star-forming region scale in the nearby galaxy is the lack of the photons. Here again, M83 Chandler image shows really, this is like really wonderful quality of data, and you can see a lot of the structures after taking out these point sources, and you can actually compare it to the optical morphology. And here I have the and then again, if you zoom the region, you can see some of the structures, and middle is the H alpha image, and the right is the neutral hydrogen image, and contour is the X-ray, and you can see some of the structures in those like not completely related, but there is a structure along the star-forming activity. So for example, hot gas occupies star-forming region and interim region, field voids and infrared bubbles. The typical scale of these structures are from 10 to 200 parsec, but unfortunately, several nearby galaxies have only several nearby galaxies have deep Chandler exposures, and even with these galaxies, the bright end of the star-forming region have reasonable signal-to-noise ratio for the spectral analysis. So we really need a high spatial resolution telescope with the large effective area like AXIS to increase sample numbers to perform statistical analysis and characterize the X-ray signature of the stellar feedback on the star cluster scale. Here is the comparison of the 150 kilosecond of the AXIS to the Chandler. So with the same exposure, the AXIS will start showing a lot of detailed structures. And then right image is the composite image of the HST and AXIS, showing that the hot gas is filling or along with the HS scale of the star-forming activity and trace, star-forming activity. So with AXIS, we can characterize the hot gas properties of the H2 region or star clusters as a function of the star cluster mass and age. And we will then compare with them the galactic structures to determine condition for the breakout or outflow. A unified model of stellar feedback must be able to predict or explain the relationship between hot and cold gas in diverse set of the environment and over several order of magnitude in scale length. So the slightly moving on to the different science case, the relationship between hot and cold gas in the galactic outflow is the big missing piece to the answering the fundamental questions like where does the cool outflow gas come from? Do hot wind drive outflow? How important are the cosmic rays and when? What impact do outflow have on galaxies? We will also study the hot and cold extraplanar gas relationships with axis, investigating filaments in nearby edge of galaxies. So here is the M82 image of the HSD and the Chandler. The H alpha here, the right is the zoomed in the image of the central like wind region. Red is the H alpha showing a mini filament, and blue has the hot gas a bit offset from the H alpha filament. I note that those filament structure study is probably only currently the M80 Chandler data is the only data that we can do finding the filaments and the spectral analysis. But normal galaxy also, some of the normal galaxy also show filament-like features. This is the NGC 891. Here, the small box, this small box zooms image is the right side. Shows the structure on the H alpha and X-ray above the galactic disk. X-ray and H alpha filaments are generally, well, X-ray and H alpha are generally bright in the same region, but there are clear differences in H alpha structure and X-ray structures. Sometimes filament can have slightly different spectral properties compared to surrounding diffuse gas. So studying the filaments may help quantify the relationship between the cool and hot gas, such as the cool cloud formation and evaporation models and emission mechanism indication of the charge exchange or shock heated gas. Again, these features are very dim and structured. The usually 50 parsec scale is a very small scale. So we will need a telescope like AXIS. So now I will shift to X-ray binary feedback. This is the simulated LICOM maps of the 21 centimeter brightness temperature offset from the cosmic microwave background and the reach of the second generation 21 centimeter interferometers for two different models. Top one is LX SL4 star formation rate scaling set from local starburst galaxies, and the bottom one is a more extreme X-ray model that is both more luminous and harder spectrum. The epoch of heating is this bottom scenario is abrupt, and then the structure at the reionization is less patchy. We emphasize that both the shape of the spectrum and normalization LX over SFR is important for these cosmological milestones. X-ray binary may be important not only for epoch of heating through direct influence of the X-ray photons, on the IgM, but also during the epoch of the reionization through production of the ionizing photons or facilitating escape of the ionizing photons from some of the outest galaxies. In fact, the population synthesis model accounting for binary evolution and the shift evolution of the star formation rate and the metallicity predict high mass X-ray binaries may dominate X-ray emissivity at the high X-ray emissivity at the high redshift. Critically, however, we do not have a direct constraint on X from normal galaxy as a function of redshift. So this redshift 2 is a current channel limit, and the axis could so this is a potential discovery space one axis constraining the redshift range between 2 to 8. And here the one of the model between this redshift range, one of the model predicted the emissivity of the AGN draw down to the high mass X binary. AGN is more than AGN. High mass X binary emissivity more than AGN X emissivity, and we might able to, with axis, we might able to get empirical result for this model. So here we came up with 2 observational plans. One is for the nearby galaxy survey, including both face-on and edge-on. We were working on 10 to 100 parsec scale structures. Our sample will, so this is very nearby, like the very smaller scale, so we have to limit to the distance somewhere like 10 megaparsec, and the sample will be combined with various galaxy types. Mass and specific star formation. So, and this work will require good multi-wavelength coverage. So we will look into the Vegas galaxy or SDS, or local volume mapping galaxy, or changes galaxies to get the best sample. We are still working on choosing the best sample with the simulation. And so we try to get about like the 1,500 star clusters and 100 filaments to do the statistical study. And currently we are estimating total of the 2 megaseconds for phase 1 and 1 megasecond for the edge-on galaxy study. For X-ray binary feedback case, the observational criteria is the flux down to the confusion limit, which is about 10 to the minus 18 ergs per second centimeter square. And that is about 6 megasecond. Exposure corresponding to the shift up to 8. So here the number with estimate with axis with 6 megasecond exposure, axis will find 600 galaxies between redshift of the 4 to 8, which is very exciting. And this is something that we can do using the deep field data. The summary of the stellar feedback science case is we do not understand well how the stellar feedback interplay with the ISM, which is the weakest link in the theory of the galaxy formation and evolution. At the high redshift, it extends to the uncertainties in the sources responsible for ionizing the universe. By combining spectral and imaging capabilities, AXIS enable us to understand the nature of the diffuse X-ray emission from nearby galaxies, which determine the effectiveness of the stellar feedback in regulating ISM and CGM, and track the tracing of the X-ray binary feedback across the cosmic time, which may probe important regulating how the reionization proceeded in the early universe. Good accounting of the feedback requires panchromatic view, and X-rays are an integral piece of this for quantifying energy in stellar and X-ray feedback, including both radiating and mechanical. So this panchromatic view of feedback is called out in a decadal. AXIS would be matched in the resolution of the H alpha and UV imaging capability of nearby galaxies, while also providing spectral information in the model-like exposure time owing to effective area and low background. Only AXIS was able to map LX over SFR, scaling for normal galaxies out to the high redshift, complementary to the range JWST will probe. So here, this is the end of my talk. Thank you.
Okay, great. So let's see, do we have any questions? Feel free to raise your hand or write a question in the chat. Those simulations, Mihoko, and the images were really great. It was really great to see. I was curious how, when you're doing these surveys, if sort of, you'll come back to these many times, if variability in these sources is important, or it's more just detecting these sources for the first time, you can get the intrinsic sort of distribution out to high redshift, or I'm just curious about that.
I think the detection, like first is detection. I think really those are dim source, and I think really need to do the like long exposure. I think Brett, maybe call Brett and then Christina on the call, maybe they have more better explanation and interpretation of science. So if they want to speak up, please do so.
Sorry, okay, so maybe I can, so sorry, Mike, is a question that for like, so maybe I can, so I'm getting bad feedback. Is anyone else hearing that? No? Okay. Is the question about a deep field survey, is there a concern about variability for detections?
Oh, I was just wondering if that's interesting at all in that type of source population or not, or if it matters, or I was just curious since you'll have many different epochs or.
Yeah, absolutely. So I think what nearby studies have shown are that, of course, like your low and high mass X-ray binary populations will be highly variable, but in an integrated sense, like the shape of the luminosity function is not changing. So especially for like a survey, if you're kind of dealing with integrated values for a population, then I think you should be getting the same kind of integrated average. So if sources are just kind of like switching spaces, maybe in luminosity space, as some things become brighter and some things become fainter. But yeah, I mean, certainly for like nearby galaxies, studying the effects of variability on, say, the luminosity functions is a interesting avenue, but it's probably not too much of a concern in how it would affect, say, a survey where you're using the population averaged values.
Okay.